the focused area. So the focused area for now is I/O, but the concepts we've talked about them time and again. Okay, so interrupt is interrupt. Earlier on, when we spoke about it, we didn't call it interrupt-driven I/O. We only mentioned it as interrupt, but it was actually coming from the I/Os, by the way. The same. Okay. And then to present an overview of the operation of direct memory access, which also we talked about, DMA, and then an overview of direct cache access, that is the only new technology here, and then explain the function and use of I/O channels. So in addition to the processor and a set of memory modules, the third key element of the computer system is a set of I/O modules. Each module interfaces to the system bus or central switch and then controls one or more peripheral devices. An I/O module is not simply a set of mechanical connectors that wire a device into the system bus, but rather the I/O module contains logic for performing a communication function between the peripheral and the bus. So the main question that maybe somebody will be asking, or you may be asking, is that why is it that we cannot connect the peripherals directly to the system bus? And there are a number of reasons why we cannot do that. One, there are a wide variety of peripherals with various methods of operation. It would also be impracticable, therefore, to incorporate the necessary logic within the processor to control this range of devices, of diverse devices. And then the data transfer rate of peripherals is often much slower than that of the memory or the processor. And therefore, it is again impracticable to use the high-speed system bus to communicate directly with a peripheral, which is slow. Another reason, on the other hand, the data transfer of some peripherals is faster than that of the memory or the processor. Again, there's going to be a mismatch that would lead to inefficiencies if not properly managed. So whether it's because it's slow or whether it's because it's faster than the processor, we need to manage it properly because of mismatch. And then the peripherals often use different data formats as well as word lengths than the computer to which it's attached. So therefore, as you can see, the I/O module is required to be able to manage as an interface between the system bus. So that's what we see here. So that's the system bus, and that's the I/O. And then you have a number of peripheral devices, or peripherals as we call them. Okay. So as you can see in this figure, there is two interfaces, two major functions. And we have the interface to the processor and the main memory via the system bus or the central switch. And then the interface to one or more of the peripheral devices by tailored data links. So these are depending on what device is connected. This link may be different. It may be a parallel link, it may be a serial link. So that's what we mean by tailored or custom link, data links. So we begin this session with a brief discussion of external devices and followed by an overview of the structure and function of the I/O module. And then we will look at the various ways in which the I/O function can be performed in cooperation with the processor and the main memory, which we call the internal I/O interface. And then we would also examine in some detail direct memory access and the more recent innovation, direct cache access, DCA. And finally, we will examine the external I/O interface between the I/O module and the outside world. So we proceed by looking at the external devices. The I/O operations are basically accomplished through a wide assortment of external devices that provide a means of exchanging data between the external environment and the computer. An external device attaches to the computer by a link to an I/O module, which as you saw in the figure 7.1 previously. So the link is used to exchange control, status, and data between the I/O module and the external device. An external device which is connected to the I/O module is often referred to as the peripheral device or simply a peripheral. So we can broadly classify external devices into three. We have human readable, which is basically suitable for communicating with the computer user. We have machine readable, which is suitable for communicating with equipment. And then we have communication, which is suitable for communicating with remote devices. Now, typical examples of the human readable devices are the video display units, VDUs, or video display terminals, VDTs, basically same, and also printers. And then examples of machine readable devices are magnetic disk and tape systems, as well as sensors and actuators, such as are used in robotic applications and IoTs and so on and so forth. Note that we are viewing the disk and the tape systems here as I/O devices in this lesson, whereas previously, I think it's even last week, when we discussed the magnetic tape and the disk systems, we view them as memory devices. Okay, if you recall, external memories. And from a functional point of view, these devices are actually part of memory hierarchy, and their use is appropriately described under the external memory, which we did last week. Again, from a structural point of view, these devices are controlled by the I/O modules, and therefore they can also be considered here as I/O devices. Okay. Now, with regards to communication devices, it allows for a computer to exchange data with a remote device, which may be a human readable device such as a terminal, or a machine readable device, or even with another computer. In very general terms, the nature of an external device is as depicted in this block diagram, which shows some control signals, status signal, data signals, and so on. So the moment you see this, then you know where it's interfacing to, interfacing with the I/O module, and then to the external environment. Okay, so this is a typical block diagram of an external device. So here the interface to the I/O module is in the form of control, data, and status signals. The control signals determine the function that the device will perform, such as send data to the I/O module, in which case we call it inputs, or a read operation, or accept data from the I/O module, in which case we call it outputs, or a write operation. As well as it can also report status or perform some control function particular to the device. For example, to position a disk head. So data are in the form of a set of bits to be sent to or received from the I/O module. Now, the status signal indicates the state of the device. Typical examples are ready or not ready, to show whether the device is ready for data transfer or not. Okay. Now, in respect of the control logic, it is associated with the device control, the device which controls the device's operation in response to the direction from the I/O module. And then it has the transducer. The transducer actually converts data from electrical to other forms of energy during an output operation, and from other forms of energy to electrical energy during input. So typically, a buffer is also associated with the transducer to temporarily hold data that is being transferred between the I/O module and the external environment. Why do we need this? Again, because of variation in formats and in speed. Okay, so the buffer is necessary. So when you depress the key, it is kept first in a temporary buffer, so that necessary adjustment in terms of speed, in terms of data formats, could be done within the buffer before it is further transmitted or executed. Now, a typical buffer size of about 8 to 16 is common for a serial device, whereas block-oriented devices such as disk drive controllers may have much larger buffers. The interface between the I/O module and the external device will be further examined in due course. Now, the interface between the external device and the environment is actually beyond the scope of our lesson. And so we will skip that, but we'll give some generic examples as we go along. Our first example is the keyboard monitor. The most common means of computer user interaction is the keyboard monitor arrangement. The user provides input through the keyboard. The input is then transferred to the computer and may also be displayed on the monitor. In addition, the monitor displays data provided by the computer. Now, the basic unit of exchange is the character. Associated with each character is a code, typically 7 or 8 bits in length. The most commonly used text code is the International Reference Alphabet, IRA. Here, each character in this code is represented by a unique 7-bit binary code. And therefore, we can have 128 different characters that can be represented using this IRA code. So characters are of 2 types, either printable or control. The printable characters are the alphabetic, the numeric, as well as special characters that can be printed on a paper or on a screen. Some of the control characters have to do with controlling the printing or displaying of the characters. For example, the carriage return or the enter key. Okay. There are others like the caps lock, which would change the nature of the character itself. So if we use the caps lock, it would change it from, say, a small case to a big case, capital letters. Okay. So other control characters are concerned with communications procedures. For the keyboard input, when the user depresses a key, for example, this generates an electrical signal that is interpreted by the transducer in the keyboard and then translated into the bit pattern of the corresponding IRA code. This bit pattern is then transmitted to the I/O module in the computer. At the computer, the text can be stored in the same IRA code, or on the outputs, the IRA code characters are transmitted to an external device from the I/O module. The transducer at the device interprets this code and sends the required electronic signals to the output device, either to display the indicated character or perform the requested control function. Typical transducers, there are a number of transducers that we use even in our daily lives. Very typical one, as we are even having this lecture, I'm making use of a transducer called microphone. It changes sound energy to electrical energy. So as I speak into the microphone, sound energy is converted into electrical pulses. And then this is amplified and sent, in other words, formatted, and then sent to the output. So the output is based on whatever. So even in this particular one, it will go through the internet link and so on, wherever you are. And when you receive it, the computer will receive it, gets it from electrical signal to another transducer, which is your speaker. Okay, so that is how come you would hear it, because there is a transducer involved in interpreting this sound energy that was converted into some electrical pulses that was boosted, because we have to transmit it over the line. It has to be amplified to some level. Other than that, it would have faded off by the time it reaches wherever you are. Okay, so that's about the transducer. There are a number of transducers. All right. So the disk drive, for example, contains electronics for exchanging data, control, and status signals with the I/O module, plus the electronics for controlling the disk read or write operation or mechanism. In a fixed head disk, for example, the transducer is capable of converting between the magnetic patterns on the moving disk surface and the bits in the device's buffer. A moving head disk must also be able to cause the disk arm to move radially in and out across the disk surface. So we look at the I/O modules, its function. The major functions or requirements of an I/O module fall into the following categories. We have control and timing, processor communication, device communication, data buffering, and error detection. Now, during any period of time, the processor may communicate with one or more external devices in an unpredictable patterns, depending on the program's need for IO device or resource. The internal resources, such as the main memory and the system bus, must be shared among a number of activities, including the data IO itself. Therefore, the IO function includes control and timing requirement, which actually is to coordinate the flow of traffic between the internal resources and the external devices. For example, the control of the transfer of data from an external device to the processor might involve the following sequence of steps. So first of all, the processor interrogates, in fact, we're going to revisit this in a flowchart. The processor interrogates the IO module to check the status of the attached device. Is there a device attached? For example, a printer. Is there a printer attached to my machine or not? The processor would have to check. And then the IO module returns the device status. Yes, it's attached. Is it powered on or is it off? If the device is operational and ready to transmit, in which case is on and may be ready, then the processor requests the transfer of data by means of a command to the IO module. The IO module obtains a unit of data. It could be 8 or 16 bits from the external device, and this data is transferred from the IO module to the processor. If the system employs a bus system, then each of the interactions between the processor and the IO module involves one or more of bus arbitrations. The preceding simplified scenario also illustrates the IO module must communicate with the processor and the external device, and therefore we have processor communication, which actually involves command decoding, data status reporting, as well as address recognition. So the IO module accepts commands from the processor, typically sent as signals on the control bus. For example, an IO module for a disk drive might accept the following commands: either read sector or write sector, seek track number, as well as scan record with ID number, so and so. So as you can see, the latter two commands each include a parameter that is sent on the data bus. So whether it is seek track number, so and so, or scan record ID, so and so. Okay. And then the data. So the data are exchanged between the processor and the IO module over the data bus. And then status reporting. Because the peripherals are generally so slow, it is important to know the status of the IO module. For example, if an IO module is asked to send data to the processor, in which case it's a read operation, it may not be ready to do so for a number of reasons, either because it is still working on the previous IO command that was issued to it, or simply not ready. This fact can be reported with a status signal, and common status signals are, for example, busy and ready. Okay. And there may also be other signals to report various error conditions as well. So if you're dealing with a printer, first of all, the processor has checked and there's a printer attached, it is on, but there's no paper. So if there's no paper, it cannot print. So the IO, through the IO module, this printer will communicate to the processor that there is no paper, or there's a paper jam, or in more intelligent, they can even tell you the ink level, or the cartridge level, or the toner level, and so on and so forth. Then the address recognition. Just as each word of memory has an address, so does each IO device. And this fact we know already. You recall when we talked about, I use example of pen drive. When you attach a pen drive, from lay perspective, it will be installing what do we call it? A driver. It will be installing drivers for the system. But from computer architect's perspective, it will be assigning an address in memory to this device. Okay. Therefore, an IO module must recognize one unique address for each peripheral that it controls. On the other side, the IO module must also be able to perform device communication. This communication involves command, status information, as well as data. An essential task of the IO module is also data buffering. And I think I already gave you the good reasons already. The need for this function is apparent. For example, whereas the transfer rate into and out of the main memory or the processor is quite high, the rate is in the orders of magnitude that is lower for many peripheral devices and covers a wide range. So data that is coming from main memory are sent to an IO module in a rapid burst. The data are buffered in the IO module and then sent to the peripheral device at its data rate. Okay, because even for us using the keyboard, there are some of us who will be doing A wahin, B wahin, where is A, where is B, in one by one. So can you imagine if the processor was not buffering this before displaying or executing whatever it's supposed to do, as against the person who is a very fast typist. So such a person will be typing very fast. But because of the buffer, nothing bad untoward will happen. Okay. So in the opposite direction, the data are buffered so as not to tie up the memory in a slow transfer operation. Therefore, the IO module must be able to operate at both device and memory speeds. Similarly, if the IO device operates at a rate higher than the memory access rate, then the IO module performs the needed buffering operation as well. Finally, the IO module is often responsible for error detection and for subsequently reporting errors to the processor. One class of errors include mechanical and electrical malfunctionings reported by the device. For example, like, as I mentioned, paper jam or bad disk track or no paper and so on. Another class also consists of unintentional changes to the bit pattern as it is transmitted from device to the IO module. Some form of error detecting code is often in use to be able to detect transmission errors. In our study or throughout our study, we've talked about a number of them. if you recall, we talked about Hamming code, and we said that the mathematics of it is beyond our level, so we left it. But at least we mentioned that Hamming code could be used in other ones for error detection. We have also looked at CRC, cyclic redundancy check. And now we are looking at a simple example that is also in use called parity bit, which is used on each character of the data. So for example, the IRA character code occupies 7 bits of a byte. And you know that the byte consists of 8 bits. So the 8th bit is set so that the total number of ones in the byte is even. And when it is even, we call it even parity. Or we set it so that the total number of ones within the byte would be odd. If it is odd, we call it odd parity. So when a byte is received, the IO module checks the parity to determine whether an error has occurred or not, be it even parity check or odd parity check. So this is computed by the IO module. Now let's look at how the IO module itself looks like. So this is a typical block diagram of an IO module. You can see the IO module or modules vary considerably in complexity and the number of external devices that may be attached and therefore that it controls. We will attempt only a very generic description here. So as seen in this figure 7.3, it provides a general block diagram of an IO module. The module connects to the rest of the computer through a set of signals, for example, system bus lines, and you can see the system bus line. So this is the interface to the system bus. How do we know it's a system bus? Because it has control bus, it has address bus, and it has data bus. These 3 constitute what we call the system bus. We know this from our previous lesson, okay? So data transferred to and from the module are also buffered with the data registers. Why? We already gave the reason, if you remember, okay? So I'm not going to tell you why. And these are simple kind of, how do we call it? Brief essays. I think, yeah, that's what we call it. We call them brief essays. But it could be just a couple of lines, okay? So so there will be, I haven't set my question yet. I think I would make an attempt this weekend. It's going to have a structure of some multiple choice and some short answers, and then a number of brief essays. Okay, so people can play games with the multiple choice. You know, you can just do some guesswork, or as is done, maybe somebody will be teaching you the answer to question 1 is A, question 2 is B, question 3 is C, question 4 is D, and so on. One of the things, if we're doing it in the system, then be minded that the system is smart, so it will shuffle. I think you experienced it in the mid-semester. It will shuffle and randomize the questions. Okay, if I have the time and the luxury, I would even input more than necessary questions. So let's say you are required to answer 20 multiple choice questions. I would input, let's say, 50. in which case each of you will have their own set of 20. So you keep on giving him question 1 is A and B and so on and so forth. No problem. On the day of reckoning, we will see. Okay. I mean, sometimes just to show, to build integrity, there's nothing like you feeling confident that I did it myself. I don't know. We may be different people, but that's how I feel in life. That I want to be able to say that I did it, not buy your head in shame. Somebody help you out, or you used a paw, or whatever you call it. Anyway, anyhow. Okay. So there may also be one or more status registers that provide current status information. A status register may also function as a control register, and that is how come we have it as status control registers. And because of the control function, we'll be able to accept detailed control information from the processor. The logic within the module interacts with the processor via a set of control lines, as you can see. So that's the control lines, and that's the logic. The processor uses these control lines to issue commands to the I/O module. Some of the control lines may also be used by the I/O module, for example, for arbitration or status signals. The module must also be able to recognize and generate addresses associated with the devices it controls. Each I/O module has a unique address, or if it controls more than one external device, a unique set of addresses will be applied. Finally, the I/O module contains logic specific to the interface with each device that it controls. I think I explained that already. Some of them may be a para interface, and some may be serial interface. And even if it's the same serial interface, there may be different devices with different specifications, and so on and so forth. Okay. An I/O module functions to allow the processor to view a wide range of devices in a simple-minded way. So there is a spectrum of capabilities that may be provided. The I/O module may hide the details with regards to the timing, the formats, and the electromechanics of an external device, so that the processor can function in terms of simple read and write commands, and possibly open and close file commands. In its simplest form, the I/O module may still leave much of the work of controlling a device. For example, rewind a tape that should be visible to the processor. An I/O module, again, that takes on most of the detailed processing burden by presenting a high-level interface to the processor, is usually referred to as an I/O channel or I/O processor. We will look at it again in detail. An I/O module that is quite primitive and requires detailed control is usually referred to as an I/O controller or device controller. I/O controllers are commonly seen on microcomputers, whereas I/O channels are used on mainframes. In what follows, we will use the generic term I/O module when no confusion results, and will use more specific terms where necessary. So now we look at programmed I/O. 3 techniques are possible for I/O operations. With programmed I/O, data are exchanged between the processor and the I/O module. And again, like I reminded you, these, we've talked about them before. We are only having an abstraction from I/O perspective. In other words, most of these concepts are going to be repeated, okay, or things that we've met before. So the processor executes a program that gives it direct control of the I/O operation. During sensing device status, sending a read or write command, as well as transferring the data. When the processor issues a command to the I/O module, it must wait until the I/O operation is complete. If the processor is faster than the I/O module, this is a waste of time for the processor. With interrupt-driven I/O, the processor issues an I/O command, and then it continues to execute other instructions and is interrupted by the I/O module when the I/O or the latter has completed its work. With both programmed and interrupt I/O, the processor is responsible for extracting data from the main memory for output and storing data in the main memory for input operations. The alternative is known as direct memory access, DMA. In this mode, the I/O module and the main memory exchange data directly without necessarily involving the processor, actually at the permission of the processor. We talked about this. So the table, this table actually depicts the relationship amongst these three techniques. And it makes a comparison using these two parameters, the I/O to memory transfer through the processor, where there's no interrupt, it's programmed I/O, and where there's an interrupt, we call it interrupt, or more specific, interrupt-driven I/O. So if you recall, when we met it the first time, we simply called it interrupts, okay? Where we varied the instruction cycle. And then in a direct I/O to memory transfer under the permission of the processor, we call it DMA, direct memory access. Now, so we can look at some I/O commands. So there are 4 types of I/O commands that an I/O module may receive when it is addressed by a processor. So we have control, we have test, we have read, and of course, write. So for the control, it is used to activate a peripheral and tell it what to do. For example, a magnetic tape unit may be instructed to rewind or to move forward 1 record. These commands are tailored to the particular type of peripheral device. We said this before, okay? That's when we describe the I/O module, the devices attached to it with tailored data links. The reason, so that could also be another question, for example, why does, or why, I don't know how I'll phrase it, but in simple terms, why does the peripheral device connect to the I/O module using tailored or customed data links? Simple reason, because each of them have their peculiar formats and peculiar word lengths as well as operations. Very simple. And then we have the test command, which is used to test various status conditions that are associated with an I/O module and its peripherals. The processor will want to know that the peripheral of interest is powered on, like I explained with the printer. Is it powered on or is off? And therefore also available for use or not. It will also want to know if the most recent IO operation is completed or if any errors had occurred along the line. For example, you issue a print command, and after printing, it's supposed to print 20 pages. After printing 18 pages, maybe there's no more toner or ink, or there's a paper jam, or there's no paper. So it has to report to the processor that an error has occurred. What sort of error? No paper, or paper jam, or whatever it is, or maybe there's a power cut along the line. So all these will be reported. Okay. Now we have read command. The read command actually causes the IO module to obtain an item of data from the peripheral and to place it in an internal buffer that was depicted in the diagram to us. The processor can then obtain the data item by requesting that the IO module place it on the data bus. Similarly, there is the write command that causes the IO module to take an item of data, be it a byte or a word, from the data bus and subsequently transmit that data into the peripheral. So as seen in this figure 7.4a, it gives an example of the use of a programmed IO to read in a block of data from a peripheral device. For example, a record from a tape into the memory. Now, data are read in one word, for example, 16 bits at a time. And for each word that is read in, the processor must remain in a status checking condition. Status checking. Where is my cursor? Here. So status checking. So it keeps checking. So assuming whenever it checks, it's not ready, something is not ready, or an error has happened. So all this time is a waste of time, for precious time for Mr. Processor. Okay? You get that? Status checking cycle until it determines that the word is available in the IO module's data register. In other words, the buffer. So this flowchart highlights the main disadvantage of this programmed IO technique. It is time-consuming process that keeps the processor busy needlessly. Okay, so we would revisit the interrupt-driven as well as the DMA. Indeed, we have talked about these before. We've seen this flowchart before, but let's go on. So in respect of IO instructions, with programmed IO, there is a close correspondence between the IO-related instructions that the processor fetches from memory and the IO commands that the processor issues to an IO module to execute the instructions. That is to say that the instructions are easily mapped into an IO module or IO module, IO commands, and there is often a simple one-to-one relationship. So the form of the instruction actually depends on the way in which the external devices are addressed. So typically, there will be many IO devices connected to through the I/O modules to the system. Each device is given a unique identifier or address, as we know. When the processor issues an I/O command, the command contains the address of the desired device in question. Therefore, each I/O module must interpret the address lines to determine if the command is for itself or not. When the processor, main memory, and the I/O share a common bus, two modes of addressing are possible. We have memory mapped I/O as well as isolated I/O. With the memory mapped I/O, there is a simple address space for memory locations and I/O devices. This processor, the processor treats the status and the data registers of the I/O modules as memory locations and uses the same machine instruction to access both memory and the I/O devices. So for example, with 10 address lines, a combined total of 2 to the power 10, which is equal to 1K or 1024 memory locations and I/O addresses can be supported based on any combination of our choice. Now, with memory mapped I/O, a single read line and a single write line are needed on the bus system. Alternatively, the bus may be equipped with memory read and write plus input and output command lines. The command line specifies whether the address refers to a memory location or an I/O device. The full range of addresses may be available for both. Again, with the 10 address line example, the system may now support both, say, 1024 memory locations as well as 1024 I/O addresses for the devices. Now, because the address space for I/O is isolated from that of the memory, this is referred to as isolated I/O. Very simple concept. So, okay. So there are a number of ways of explaining this. Another example will be, for example, using a terminal keyboard that might appear to the programmer using a memory mapped I/O. So again, assuming a 10-bit address with a 512-bit memory locations numbered from 0 to say 511 and up to 512 I/O specific addresses for the devices. In this case, locations 512 to 1023. Okay, mind you, we have a total of 1024. So we start from 0 to 1023. And then we've divided it. So there are memory locations in a memory mapped, in isolated I/O. So we have 0 to 512 and 512 to 1023. So two addresses are dedicated to the keyboard input from a particular terminal. So address 516 refers to, I think we have this, no, I'm going back. Okay, so this explained when I spoke about the memory mapped and then the I/O isolated. So actually, this is what I'm referring to now as an example with the keyboard input status and so on. Okay, so address 516 is referring to data register. And then address 517 refers to the status register. which also functions as the control register for receiving the processor commands. Now, the program shown will read 1 byte of data from the keyboard into an accumulator register in the processor, and that is what is shown here. So the 516 load accumulator, that is what has been assigned in this particular program. And so if you recall, when we did the computation, I told you that the instructions or the operands that we have assigned were specifically for that particular assignment. It doesn't mean that all the time one would be for this or that. Okay. All right. Good for that clarification once more. Even though I'm not quite sure, implementing that kind of computation has always been my favorite. And of course, I guess favorite for some good students, because once you understand that, you have 12 points banked for free. Okay, you already has banked. In fact, usually I will do a second one, which takes the form of just looking at only the registers, and that takes another 9 points. So if you're able to answer that portion, you have a cool 20 points banked. Anyways, I'm not sure how I'm going to implement that online, but if I'm able to figure out, that would resurface. Okay. So please, when you are revising, revise that, because you never can tell. I mean, as for computer system, it may be able to help me execute that. And once it can help me execute that, I'm going to implement it. Okay. A word to the wise, they said it's from the north. Maybe now we've divided it, so maybe from Savannah. Okay. All right. So the program will show read 1 byte of data from the keyboard into the accumulator register in the processor. And we note that the processor loops until the data byte is available, which we said already. So with isolated I/O, which is shown in the B, the I/O ports are accessible only by special I/O commands, which activate the I/O command lines on the bus. And for most types of processors, there is a relatively large set of different instructions for referencing memory. If isolated I/O is used, there are only a few I/O instructions. Therefore, an advantage of memory map is that this large repertoire of instructions can be used, allowing for more efficient programming. But the disadvantage is that valuable memory address space is used up. Both memory mapped and isolated I/O are in common use. Okay. Now let's look at interrupts or interrupt-driven I/O. The problem with the programmed I/O is that the processor has to wait a long time for the I/O module of concern to be ready for either reception or transmission of data. The processor, while waiting, must repeatedly also interrogate the status of the I/O module. So it has to be checking, status checking cycle. As a result, the level of the performance of the entire computer system will be severely degraded. An alternative is for the processor to issue an I/O command to a module and then go on to do some other useful task. The I/O module will then interrupt the processor to request service when it is ready to exchange data with the processor. So the processor then executes the data transfer as before, and then resumes its former processing, user processing. That's what we called it the first time we encountered the interrupt. We called it user user program or user processing. Here, let us consider how this works. First, from the point of view of the I/O module. So for inputs, the I/O module receives a read command from the processor. And this is shown here. A read command from the processor. The I/O module then proceeds to read data in from an associated peripheral. Once the data are in the module's data register, the module signals an interrupt to the processor over a control line. The module then waits until its data are requested by the processor. When the request is made, the module places its data on the data bus and is then ready for another I/O operation or instruction. From the processor's point of view, the action for input is as follows. The processor issues a read command. It then goes off and does something else. For example, the processor may be working on several different programs at the same time. At the end of each instruction cycle, the processor checks for interrupts, as we saw in the modified instruction cycle, if you recall. At that time, we had the basic instruction cycle, which is actually consisting of a fetch cycle and execute cycle. And then we modified it when we introduced interrupts, which we are now calling interrupt-driven I/O. Okay, it's the same interrupt. We are only focusing from the perspective, from the abstraction of inputs, outputs. Okay, so it keeps checking. Now, when the interrupt from the I/O module occurs, the processor saves the contents or the context of the program that it was executing within the program counter and the processor registers of the current program. And then it processes the interrupt. In this case, the processor reads the word of data from the I/O module and stores it in memory. It then restores the context of the program it was working on or some other program and resumes execution. So as seen in the previous 7.4b, this is 7.4b. What is the case? 7.4b. So this is the interrupt driven, okay? Okay. So the interrupt I/O is more efficient than the programmed I/O because it eliminates needless waiting times for the processor. However, the interrupt I/O still consumes a lot of processor time because every word of data that goes from the memory to the I/O module or vice versa, from the I/O module to the memory must pass through the processor. So we look at the interrupt processing. So let's say we consider this in more detail. The occurrence of an interrupt triggers a number of events, both in the processor hardware as well as the software. So from this figure 7.6 or 7.6, it shows a typical sequence of what happens within this flowchart. When an I/O device completes an I/O operation, the following sequence of hardware events occurs. 1, the device issues an interrupt signal to the processor. The processor finishes execution of the current instruction before responding to the interrupt. The processor tests for an interrupt and determines that there is one. and sends an acknowledgement signal to the device that issued that particular interrupt. Now, the acknowledgement allows the device to remove the interrupt signal that it had issued. The processor now needs to prepare to transfer control to the interrupt routine. To begin, it needs to save information needed to resume the current program at the point of interrupt. So the minimum information required is either the status, not either, it's both. The status of the processor, which is contained in the register called program status word, PSW, and the location of the next instruction to be executed, which is actually contained in the program counter, as we know. So these can be pushed onto the system control stack. The processor now loads the program counter with the entry location of the interrupt handling program that will respond to this interrupt. So depending on the computer architecture and the operating system design, there may be a single program or one program for each type of interrupt, or even a program for each device or and each type of interrupt. So if there is more than one interrupt handling routine, the processor must be able to determine which one to invoke. This information may have been included in the original interrupt signal request, or the processor may have to issue a request to the device in question that issued the interrupt to request for the needed information. Once the program counter has been loaded, the processor proceeds to the next instruction cycle, which begins with an instruction fetch. Because the instruction fetch is determined by the contents of the program counter, the result is that the control is transferred to the interrupt handler program. The execution of this program results in the following operations. First of all, at this point, the program counter and the PSW, the program status word register, relating to the interrupted program, have been saved on the system control stack. However, there is other information that is considered part of the state of the executing program. In particular, the contents of the processor registers need to be saved because these registers may be used by the interrupt handler. So all of these values plus any other state information need to be saved. Typically, the interrupt handler will begin by saving the contents of the registers in the stack. Okay. The interrupt handler next processes the interrupt. So this includes an examination of the status information that is relating to the IO operation or other event that caused this particular interrupt. It may also involve sending additional commands or acknowledgements to the IO device. Again, when interrupt processing is complete, the saved register values are retrieved from the system stack and restored to the registers. The final act is to restore the PSW, the program status word, and the program counter values from the stack. As a result, the next instruction to be executed will be from the previously interrupted program. Now, we note that it is important to save all the state information about the interrupted program for later resumption. This is because the interrupts is not a typical routine that is called from within a particular program. Rather, the interrupt can occur at any time and therefore at any point in the execution of the user program. So its occurrence, its occurrence is unpredictable. Its occurrence is unpredictable. Indeed, as we will find out along the line, these two programs may not necessarily have anything in common or may even belong to completely different users. Okay. Now we look at some design issues. Okay. So two design issues arise in implementing the interrupts IO. First, because there will almost invariably be multiple IO modules, how does the processor determine which device issued the interrupt in question? Secondly, if multiple interrupts have occurred, how does the processor decide which one to process? Let's consider device identification and use that to answer these questions, these design questions that have been posed. Now here, there are four general categories of techniques that are in common use. We have multiple interrupt lines, we have software pool, we have daisy chain or hardware pool and vectored. And then we have the same vectored but bus arbitration. Now let's look at them in a bit more detail. The most straightforward approach to this problem is to provide multiple lines, multiple interrupt lines, problem solved, rather, between the processor and the IO module. So now we have more, but that's not the way to go. Again, it is impracticable to dedicate more than necessary bus lines or processor pins to the interrupt lines. The resulting effect would be that even if multiple lines are used, it is likely that each line would have multiple IO modules that are also attached to it. And therefore, one of the other three techniques that we're going to describe or that we have mentioned will probably resolve the issue. One alternative is the so-called software pool. When the processor detects an interrupt, it branches to an interrupt service routine that pulls each IO module to determine which module caused the interrupt. The pool could be in the form of a separate command line, for example, test IO. In this case, the processor raises the test IO command and places the address of a particular IO module on the address lines. The IO module responds positively if it's the one that sets that particular interrupt. Alternatively, each IO module could contain an addressable status register. The processor then reads the status register of each IO module to identify the interrupting module. Once the correct module is identified, the processor branches to the device-specific service routine of that particular device. But the disadvantage here is that the software pool is also time-consuming. I'm sure you could guess that's very time-consuming. So a more efficient technique is to use the daisy chain, which provides, in effect, a hardware pool. We saw the daisy chain. We call it nested interrupts. Okay. In the previous life, we called it nested interrupt, but it's the same daisy chain. An example of a daisy chain configuration was shown to us in our previous life. So for interrupts, all I/O modules share a common interrupt request line. The interrupt acknowledge line is daisy chained through the modules. When the processor senses an interrupt, it sends out an interrupt acknowledge. This signal propagates through a series of I/O modules until it gets to the requesting module. The requesting module typically will respond by placing a word on the data lines. This word is what we refer to as a vector and is either the address of the I/O module or some other unique identifier. In either case, the processor uses this vector as a pointer to the appropriate device service routine. And this avoids the need to execute a general interrupt service routine first. And so this technique is called a vectored interrupt. There's another technique that makes use of vectored interrupts as well. That is the bus arbitration. With the bus arbitration, an I/O module must first gain control of the bus before it can raise the interrupt request line. This is akin to what we have in our datacom or networking with regards to token rings and some of the bus configurations, in which with the token ring, before you transmit, you would have to seize the channel or the circuits or the bus by putting forth your token, okay? So some of the concepts, they are not different from each other. In fact, even talking about bus arbitration, in your datacom, you also do arbitration as well to avoid collusion. So it has to be collusion sense and collusion avoidance and detection and so on and so forth. Okay. So the aforementioned techniques serve to identify the requesting I/O module, and they also provide a way of assigning priorities when more than one device is requesting interrupt service. With multiple lines, the processor just picks the interrupt line with the highest priority. With software pooling, the order in which modules are pooled determines their priority. Similarly, the order of modules on a daisy chain determines their priority. And so finally, the bus arbitration can employ a priority scheme. Okay. So we continue by looking at some drawbacks with regards to the program I/O and the interrupt-driven I/O. Actually, all these we have discussed them time and again, okay? Except that, so we are putting more emphasis on it, basically. Now, in terms of the drawback, we cast our mind back, we cast our mind back to the interrupt-driven I/O. Though more efficient than the simple programmed I/O, it still requires the active intervention of the processor to transfer data between the main memory and the I/O module, and any other data transfer must also pass through the processor. Therefore, these forms of I/O suffer from two inherent drawbacks. First, the I/O transfer rate is limited by the speed with which the processor can test and service the device. Secondly, the processor is tied up in managing the I/O transfer. And in a situation where a number of instructions must be executed for each particular transfer, then more waste of time. So there is somewhat a trade-off between these two drawbacks. Consider a transfer of a block of data. Using simple programmed I/O, the processor is dedicated to the task of the I/O and can move data at a rather high rate at the cost of doing nothing else. The interrupt I/O frees up the processor to some extent at the expense of the I/O transfer rate. Nevertheless, both methods have an adverse impact on both the processor activity and the I/O transfer rate. So when large volumes of data are to be moved, a more efficient technique is employed, which is direct memory access, DMA. Now let's look at how the DMA works. The DMA basically involves an additional module on the system bus. The DMA module, as depicted in this block diagram in 712, is capable of mimicking the processor and indeed of taking over control of the system under the permission of the processor. It needs to do this to transfer data to and from the memory over the system bus. Now, for this purpose, the DMA module must use the bus only when the processor does not need it, or it must force the processor to suspend operation temporarily. The latter technique, that is asking the processor to suspend its operation temporarily, is more common and is referred to as cycle stealing. Cycle stealing, because the DMA module in effect steals a bus cycle. When the processor wishes to read or write a block of data, it issues a command to the DMA module by sending to the DMA module the following information. First of all, whether a read or write is requested using the read or write control line between the processor and the DMA module. Then the address of the IO module involved is communicated on the data lines. The starting location in memory to read from or write to is also communicated to the data lines and stored by the DMA module in its address register. The number of words to be read or written, again, must also be communicated via the data lines and stored in the data count register. So the processor then continues with other work. It has delegated this IO operation to the DMA module. So the DMA module transfers the entire block of data, one word at a time, directly to and from the memory without going through the processor. So when the transfer is complete, the DMA module sends an interrupt signal to the processor. Therefore, the processor is involved only at the beginning and at the end of the transfer. So as we have in this figure 713, it shows where in the instruction cycle the processor may be suspended. In each case, the processor is suspended just before it needs to use the bus. So the DMA module then transfers one word and returns control to the processor And we know that this is not an interrupt. This is not a typical interrupt. Okay. The processor does not save a content and do something else. Rather, the processor pauses for one bar cycle. The overall effect is to cause the processor to execute more slowly. Nevertheless, for a multiple word I/O transfer, the DMA is far more efficient than the interrupts driven or the program I/O. So the DMA mechanism can be configured in a variety of ways as seen in this diagram. 714. In the first example, A, all modules share the same system bus. So the DMA module, acting as a surrogate processor, uses programmed I/O to exchange data between the memory and the I/O module through the I/O, through the DMA module. This configuration, which, while it may be inexpensive to implement, is clearly inefficient. As with the processor-controlled programmed I/O, each transfer of a word consumes 2 bar cycles. So the number of required bicycles can be cut substantially by integrating the DMA and the I/O functions as seen in figure B. So that's where you see it. So this is an integrated one, or it's connected to the DMA directly. So the figure B indicates the path between the DMA module and one or more I/O modules that it does not include the system bus directly. So the DMA logic may actually be part of an I/O module, or it may be a separate module that controls one or more of the I/O modules. These concepts can be taken one step further by connecting I/O modules to the DMA module using an I/O bus. So this is taken further. So now the DMA has different I/Os that are connected through the I/O bus. Okay, so that makes a bit of change. So this reduces the number of I/O interfaces to the DMA module to 1 and provides for an easy expandable kind of configuration using the I/O bus. In both cases, the B and the C, the system bus that the DMA module shares with the processor and the memory is used by the DMA module only to exchange data with the memory. So the exchange of data between the DMA and the I/O module takes place off the system bus, as you can see. Okay. And there are different implementations of this. So there's just one that one of the common ones implemented by Intel called flyby DMA controller. So this DMA controller is used using the buses to transfer data. So in which case the processor is idle. In a similar way, when the processor is using the bus, the DMA is idle. Now this 8237 DMA is known as a flyby DMA controller. This means that the data being moved from one location to another does not pass through the DMA chip and is not stored on the DMA chip itself. Therefore, the DMA can only transfer data between the I/O ports and the memory address, and not between two I/O ports or two memory locations. However, as explained subsequently, the DMA chip can perform a memory-to-memory transfer via a register. So in this particular 8237, it contains 4 DMA channels that can be programmed independently, and any one of the channels may be active at any particular moment. These channels are numbered from 0 to 3. There are 4 of them. So 0, 1, 2, 3. Okay. Now we take a look at the direct cache access, which I said that it's not, the concept is not different from DMA. So DMA has proved an efficient, effective means of exchanging performance, of enhancing performance of the I/O with the peripheral devices and the network I/O traffic. However, the dramatic increases in data rates for network I/O, the DMA is not able to scale to meet the increased demand. This demand is coming primarily from the widespread deployment of 10 gigabits per second and 100 gigabits per second Ethernet switches to handle massive amounts of data transfer to and from database servers and other high performance systems. A secondary but increasingly important source of traffic also comes from Wi-Fi in the gigabit range for obvious reasons. I mean, some of us sending more data, even what we are doing with video and so on. Now, network Wi-Fi devices that handle, say, 3.2 gigabits per second and 6.76 gigabits per second are becoming widely available and producing demand on enterprise systems. So here we just show how enabling the I/O function to have direct access to the cache can enhance performance, a technique that is known as direct cache access or DCA. Here throughputs, here we are concerned only with the cache that is closest to the main memory and is often referred to as last level cache. Last level cache. Last level cache. So in some systems, this will be, say, level 2 cache or level 3 cache. To begin, we describe the way in which contemporary multi-core systems use on-chip shared cache to enhance DMA performance. This approach involves enabling the DMA function to have direct access to the last level cache. Next, we examine cache-related performance issues that manifest when high-speed network traffic is processed. From there, we're going to look at several different strategies of DCA that are designated, that are designed to enhance network protocol processing performance. And finally, we'll look at the DCA approach, which is being implemented by Intel, called Direct Data I/O, DDIO, Direct Data I/O. Okay. So we continue by looking at cache-related performance issues, as we said. So network traffic is transmitted in the form of sequence of protocol blocks called packets or protocol data units. The lowest or link level protocol is typically the Ethernet, so that each arriving and departing block of data consists of Ethernet packet containing as payload the higher level protocol packet. The higher level protocols are usually the Internet Protocol IP operating on top of the Ethernet, and then the Transmission Control Protocol TCP, which is also operating on top of the IP. Accordingly, the Ethernet payload consists of a block of data with a TCP header and an IP header. For outgoing data, Ethernet packets are formed in a peripheral component, such as an I/O controller or a network interface card, NIC. Similarly, for incoming traffic, the I/O controller strips off the Ethernet information and delivers the TCP/IP packet to the host CPU. So for both outgoing and incoming traffic, the core, the main memory, and the cache are all involved. In a DMA scheme, when an application wishes to transmit data, it places that data in an application assigned buffer within the main memory. The core transfers this to a system buffer in the main memory and then creates the necessary TCP/IP headers, which are also buffered within the system memory. The packet is then picked up via the DMA for transfer via the NIC. This activity engages not only the main memory, but also the cache. So for incoming traffic, which is similar transfers between system and application buffers are required. When large volumes of protocol traffic are processed, two factors in this scenario would degrade the performance. So first of all, the core consumes valuable clock cycles, which it consumes valuable clock cycles in copying data between system and application buffers. And secondly, because memory speeds have not kept up with the CPU speeds, the core loses time waiting on memory reads and writes. In this traditional way of processing protocol traffic, the cache does not help because the data and the protocol headers are constantly changing, and therefore the cache must constantly be updated as well. So to clarify the performance issue and to explain the benefit of the DCA, a way of improving performance. So we need to look at further into the processing of the protocol traffic in a more detail concerning the incoming and the outgoing traffic. So a number of things, steps are involved actually. So for, I'm not going to go into details, but just the generic one for you to know. So in respect of the incoming, the packet arrives, the DMA module will transfer the data, including the packet descriptor, to the main memory. It must also invalidate the corresponding cache lines, if any, and so on and so forth. And then the NIC interrupts the host. So after a number of packets have been transferred, the NIC issues an interrupt to the host processor. And then there is retrieval of descriptors and the headers and so on. And then there could also be a cache miss. You recall when we talk about the cache, we explained the cache miss. So because this is new data coming in, the cache lines corresponding to the system buffer containing the new data are invalidated. Therefore, the core must stall in order to read the data from the main memory into the cache, and then the core registers as a way of update. And then the header is processed, and then the payload is transferred ultimately. So here the data portion of the packet is transferred from the system buffer to the appropriate application buffer. Similar kind of sequence of steps also occurred in respect of the outgoing. So again, the packet transfer is requested, the packet is created, the output operation is invoked, in which case it uses a device driver program to signal the DMA module that output is ready for the NIC. And then the DMA transfer goes on, and then the NIC signals completion, as well as the driver frees the buffer for other operations or commands to be accepted. So we can also look at some DCA strategies that are in use. So several strategies have been proposed for making more efficient use of the caches for the network I/O, with the general term direct cache access strategies that are applied to these. The simplest strategy is one that was implemented as a prototype on a number of Intel Xeon processors between 2006 and 2010. This form of DCA applies only to incoming network traffic. The DCA function in the memory controller, sends a prefetch hint to the core as soon as the data are available in the system memory. This enables the core to prefetch the data packet from the system buffer, therefore avoiding cache misses and also the associated waste of the core cycles. While this simple form of DCA provides some improvement, much more substantial gains can be realized by avoiding the system buffer in the memory altogether. So for specific function of protocol processing, note that the packets and the packet descriptor information are accessed only once in the system buffer by the core. For incoming packets, the core reads the data from the buffer and transfers the packet payload to the application buffer. If it has no need to access that data in the system buffer again, similarly, for outgoing packets, once the core has placed the data in the system buffer, it has no need to access that data again. So suppose, therefore, that the I/O system were equipped not only with the capability to directly access the main memory, but also of accessing the cache, then both for input and output operations will be enhanced. Then it would be possible to use the last level cache instead of the main memory to buffer packets and descriptors of the incoming and outgoing packets. So the last approach, which is a true DCA, was proposed again by Intel, and it has been described as cache injection. Cache injection. So a version of this more complete is implemented within the Intel Xeon processor line, and is referred to as direct data IO, DDIO. Okay, so we're not, and this is the diagram for it. I'm not going to spend more time on it. So I'll just proceed to some evolution and try and wrap up. Okay. Maybe let's, even though we are nearing the completion, let's pause for about 1 minute at least, so that I can have a drink or something. So please, let's take 1 minute pause. Enoch, I know you are recording, so you can pause the recording and then you resume. You can continue with your recording. So we take a look at the evolution of the IO function. So as computer systems have evolved, there have been a pattern of increasing complexity and sophistication of individual components. Nowhere is this more evident than the IO function. We have already seen part of that evolution, and that evolution is summarized here as follows. 1, the CPU directly controls a peripheral device. This is seen in simple microprocessor control devices. 2, a controller or IO module is added. The CPU uses programmed IO without interrupts. With this step, the CPU becomes somewhat divorced from specific details of external device interfaces. 3, the same configuration as in step 2 is used, but now interrupts are employed. Here, the CPU need not spend time waiting on the IO operation to be performed, thereby becoming or increasing its efficiency. 4, the IO module is given direct access to the memory via DMA, direct memory access. It can now move a block of data to and from memory without involving the CPU, except at the beginning and at the end of the transfer. The IO module is enhanced to become a processor in its own right, with specialized instruction set tailored for IO. The CPU directs the IO processor to execute an IO program in memory. The IO processor fetches and executes these instructions without CPU's intervention. This allows the CPU to specify a sequence of IO activities and also to be interrupted only when the entire sequence has been performed. 6, the IO module has a local memory of its own and is in fact a computer in its own right. So with this architecture, a large set of IO devices can be controlled with minimal CPU's involvement. A common use for such an architecture has been to control communication with interactive terminals. The IO processor takes care of most of the tasks involving the controlling of the terminals. As one proceeds with this evolutionary path, more and more of the IO function is performed without the CPU's involvement. So the CPU is increasingly being relieved of its IO-related task, thereby improving its performance. With the last two, the 5 and the 6, a major change occurs with the introduction of the concept of the IO module capable of executing a program on its own. For example, in step 5, the I/O module is often referred to as an I/O channel. In respect of step 6, the I/O processor is the term I/O processor is often used. However, both terms are on occasion applied to both situations. And in what follows, we would concentrate on the use of the term I/O channel. Okay, I/O channel. So we look at some somebody has a chat. What is it? Okay. All right. So we look at some characteristics of the I/O channels. So the I/O channel represents an extension of the DMA concept, as you can see from this I/O channel architecture. An I/O channel has the ability to execute I/O instructions, which gives it complete control over the I/O operations. In a computer system with such devices, the CPU does not execute those I/O instructions. Such instructions are stored in the main memory to be executed by a special purpose processor in the I/O channel itself. Therefore, the CPU initiates the I/O transfer by instructing the I/O channel to execute a program in memory. The program will specify the device or devices, the area or the areas of memory for storage, the priority, and then also the actions that ought to be taken for certain error conditions. The I/O channel follows these instructions and controls the data transfer. Now, two types of I/O channels are in common use. One, we have a selector channel which controls multiple high-speed devices, and at any one time, it is dedicated to the transfer of data with one of those devices. That's why it's called selector. Therefore, the I/O channel selects one device and effects the data transfer. Each device or a small set of devices is handled by a controller or an I/O module. That is much like the I/O modules we have been discussing. Therefore, the I/O channel serves in place of the CPU in controlling these I/O controllers. A multiplexer channel can handle I/O, which is the next one. A multiplexer channel can handle I/O with multiple devices at the same time. So the difference between the selector and the multiplexer handles multiple devices at the same time, whereas the selector handles one device at a time. Easy to find. And for low-speed devices, a byte multiplexer accepts or transmits characters as fast as possible to multiple devices. Okay, various implementations are possible. Now let's look at some external interconnection standards. So we're going to do just a quick familiarization. So I'll run through them quickly of some external interconnection standards. So the first one we look at is the Universal Serial Bus, famously known as USB. So it's widely used for peripheral connections. It is the default interface for slower speed devices such as keyboard and some pointing devices, but it is also commonly used for some high-speed I/O, including printers, disks, drives, and network adapters, and so on. Now, the USB has gone through multiple generations, with the first generation 1.0 defined for low-speed data of about 1.5 megabits per second and a full speed rate of about 12 megabits per second. Then we have USB 2, you have USB 3, and so on. So in respect of USB 3, actually USB 2 started using what is called super speed in parallel with, it started using the super speed, incorporating the super speed. So USB 3, I'm talking about USB 3. USB 3 uses or incorporated super speed in parallel with the USB 2 bus. Okay, and it can have signaling speeds that ranges from about 5 gigabits per second, but due to some signaling overheads, it's the actual usable data rate is about 4 gigabits per second. And then we have the 3.1, which includes a faster version of the super speed called Super Speed Plus. Super Speed Plus. This transfer mode achieves a signaling rate of about 10 gigabits per second and a theoretical usable data rate of about 9.7 gigabits per second. So a USB system is controlled by a root host controller, and it attaches a number of devices to create a local network with a hierarchical tree topology, for example. And then we have FireWire serial bus. The FireWire was developed as an alternative to the SCSI, small computer system interface, to be used on smaller systems such as personal computers, workstations, and servers. The objective was to meet the increasing demands for high I/O rates, high-speed I/O rates, and then on these systems, while avoiding the bulky and expensive I/O channel technologies that were developed for the mainframe computers and supercomputer systems. So the IEEE standard here for the FireWire is 1394, IEEE 1394, okay, for high performance serial bus, commonly known as the FireWire. Okay, and then it has various characteristics. It can take almost 1K kind of buses for interconnecting using bridges and so on. All right, like I said, I mean, these ones you can familiarize yourself with. It can take about 63 devices, connect up to about 63 devices and so on. And then the SCSI, small computer system interface, which was once the common standard for connecting peripheral devices such as disk, modems, printers, and so on, to small and medium-sized computers. Although the SCSI has evolved to higher data rates, it has lost its popularity to such competitors as the USB and the FireWire in smaller systems. However, high-speed versions of SCSI remain popular for mass memory support on enterprise systems. For example, the IBM Z Enterprise EC12 and other mainframe computers still use the SCSI. And then also a number of Seagate hard drives, hard disk drives also use SCSI. Okay. Then we have Thunderbolt. Thunderbolt is one of the most recent and one of the fastest peripheral connection technology that has been available for general purpose use. And it was developed by Intel in collaboration with Apple. So one Thunderbolt cable can manage the work previously required by multiple cables, for example. The technology combines data, video, audio, and power into a single high-speed connection for peripherals such as hard drives, RAIDs, video capture boxes, and network interfaces, and so on. It provides for up to about 10 gigabits per second throughput to in each direction, and up to 10 watts of power in the connected peripherals. The first version of the specification was released in early 2001, and it has attracted numerous vendors. For example, IBM Z Enterprise series of mainframe computers has relied heavily on InfiniBand for a number of years. The standard describes an architecture and specification for data flow among processors and intelligent I/O devices. InfiniBand has become popular interface for storage, area networking, SAN, and other large storage configurations. In essence, InfiniBand enables servers, remote storage, and other network devices to be attached to a central fabric of switches and links. The switch-based architecture can connect up to 64,000 servers, storage systems, and networking devices, and so on. Okay. Of course, PCIe, we dealt with PCIe even in more detail. Then we have SATA. SATA stands for Serial Advanced Technology Attachment. We have the Ethernet. Ethernet, predominantly wired networking technology in use in homes, in offices, in data centers, for enterprises, and then for wide area networks, and so on and so forth. We instead of using the word Ethernet, we also call it RJ45. Okay. RJ45, that is the connector that is attached to it. So yeah, the standard is sometimes referred to as RJ45. And then RJ11 is for the telephone wire or the telephone cable, okay, or connector. Okay, so again, I'm not going to go into detail of that. So this one is IEEE 802.3. Okay. And then we have almighty Wi-Fi. All of us have been using Wi-Fi. Wi-Fi, I said wire-fire, because I was talking about firewire. Wire-fire. Okay. Predominantly the wireless internet solution or technology of choice. It's again used in homes, offices, and public spaces, including vehicles, including buses, and so on, and popular spaces, hotels, recreational centers, and so on and so forth. Okay, and there's been a lot of variation in terms of generation, and those standards are 802.11. And we have had different variations or generations all the way up to what we have as of 2014, 11AC, we have 11A, we have B, N, G, AD, and so on and so forth. Okay. All right, so this is just a pictorial view of the IBM's E-Enterprise, Z-Enterprise, EC12. So again, yes, so that brings us to the end of our discussion on IO and for the week. Now, if you have any questions, let me take them. Any questions, comments, contributions, and so on? Yes. No one has any question? No contribution? No comment? Come on. Hmm? Then it makes it looks like the whole show.
Sir,
Yes.
sir, the summary itself, is it the course outline or not?
How can the summary be the course outline? Masa, how is that possible? I hope my battery is not, because I thought I charged this. It's not. I mean, there's a, have you visited the Moodle site?
I cannot. I only visited it like this semester.
For
I only
mid-semester.
visited it once.
You only
I only
visited it for
once.
mid-semester.
Oh, I go to the GTT online, but I'll check the module. Say.
No, but because you are supposed to visit the site, I have actually posted the actual course outline.
Okay.
And then for each week, there is a summarized on what we are doing and then the notes.
Okay,
so when you ask a question like this, then I'm beginning to wonder,
Okay, sir, thank you.
Visit the sites.
Okay.
You know, sometimes some of you students, you see when I say that when you come to the class, log on with your real name and all those things, anything can happen. Anything. Last week, we were doing audit with KNUST for the graduating class. And one of the questions, sometime, I mean, maybe system error or something, somebody had 0 for a course. So the professor was asking, how is that possible? That somebody can get 0? Because even when the person attends class, he's supposed to get something. You know, even in our case, we usually don't allot any marks for attendance. But in some jurisdiction, the professor will tell you attendance is 15 points or 10 points or 5 points, whatever. Participation in this is another 10 points. Doing this is 10 points, and so on and so forth. And you know, they are strict about it. But for us, you know, the reason why sometimes we don't want to do those things and we want to go strictly objective way, objective as I mean in the way of assessment. So if we execute a test, that one, if you pass, you pass, which is not the best. You know, it's not the best at all. Any other question or comment? Alfred. Alfred. Alfred, we can't hear you.
Hello, sir.
Alfred, please go ahead.
Hello, sir.
My goodness.
Hello, sir.
Alfred, go ahead.
Hello, sir.
Alfred, I said go ahead. You know, once you raise your hand and I mention your name, it means go ahead and proceed with whatever question or comment you have. But that also becomes another tussle. Hmm? Oh, that's something. Yes, any other person who has a question or comment or something? Okay, so if no one has any question, then we'll call it a day. I have another assignment to pursue, so therefore we'll see you. I have already posted the notes on site, so please visit and pick a copy for yourself. I wish you the best. Start preparing. I'm not sure what we will do. We will have a lecture next week. But what I'm saying is that I'm not sure whether it will be a kind of revision kind of discussion, forum kind of discussion. I'm not sure the type is going to take, because technically I have covered enough for the semester. You know, I mean, we could go on and introduce another topic, but we don't really need to. So I'm going to strategize what to do as I think of exams, because the head of department has issued the instruction for exams to be submitted for moderation and so on. So as I think through over the weekend on how exams is going to look like and what sort of questions to ask, it will determine what to do. Yes, Alfred. Yes, your hand is still up.
Sir, please, I wanted to ask whether the I/O channels is one of the components of the IBM system 370.
No, not only for IBM, it's generic. The I/O channels is generic. All that we've been doing, we treat generic, in other words, general components or systems, okay? And once in a while, we will give some specific example of either from Intel or IBM or some other manufacturer. But the I/O channels are generic. The key is that you develop from the DMA concept. So now at a position, at a point, if you revisit the evolution summary, you probably may get it again. The processor has now enabled the original DMA to be able to have its own memory, to be able to have its own processing. And so it can now even instruct it with a program in memory, and it assigns the specific addresses in memory, the storage area, and so on that program should address. So when the DMA has to, that is when it's referred to as this kind of process is what we call using the I/O channel. Okay?
Okay, sir.
In another term, we also sometimes call it I/O processor, because now it has the controlling powers from the processor to be able to do it. So that's why either it is called I/O processor or I/O channel. Anyway. All right,
thank you,
guys.
sir.
You're welcome. So see you guys, God willing.